An open-loop control system executes commands without ever checking the results. It is entirely blind to its environment. If an unexpected physical disturbance occurs, the system cannot adapt, and the physical objective fails. To operate in a chaotic environment, engineers rely on the closed-loop architecture. By measuring the actual output and feeding it back to the beginning, the system becomes aware of its physical state. This generates an error variable, the exact difference between where it is and where it should be. The controller instantly calculates and executes precise corrections. This architectural principle is currently scaling out of classical aerospace engineering, specifically H-infinity control, and merging directly into generative artificial intelligence to solve the severe bottlenecks in central nervous system drug discovery. Whether navigating turbulent airspace or the human bloodstream, mastering this feedback loop provides the only mathematical framework capable of achieving precise objectives under extreme uncertainty. Early closed-loop systems were linear, dealing with a single input and a single output. You measure one variable, you adjust one actuator. But modern engineering environments are multi-input and multi-output. Adjusting thrust alters pitch. Changing a single variable inherently destabilizes thousands of others across the system. To manage this compounding complexity, engineers introduce a cost function. This mathematical tool scores system performance by assigning penalties to different states. Algorithms process this cost function to calculate the least expensive path to stability, constantly balancing thousands of competing variables, like speed versus fuel efficiency in real time. As physical systems scale, from individual mechanical parts to highly complex environments, manual heuristic rules fail. They must be replaced entirely by predictive mathematical optimization. For decades, the standard control scheme was the PID controller, calculating proportional, integral, and derivative paths. But it's vulnerable to reset windup. Math may demand 150% output, but physical actuators max at 100%. The model integrates this error, detached from physical reality. To respect these hard physical constraints across multivariable systems, engineers developed optimal control frameworks, such as model predictive control and the linear quadratic regulator. This equation defines the LQR cost function. It calculates control laws analytically, minimizing state and input variances to optimize system behavior in the time domain. Yet, models are never perfect representations of reality. To prevent catastrophic failure from these discrepancies, aerospace design relies on the ultimate hardware failsafe, robust control, or H-infinity. H-infinity explicitly addresses plant uncertainty. It guarantees an aircraft remains stable even when physical components operate differently than the internal mathematical model predicts. Hardware engineers guarantee survival by minimizing the system's mathematical condition number. They design algorithms strictly to absorb physical reality. This exact optimization logic is now being transposed onto the most uncertain physical system known to science, the human central nervous system. Engineering therapeutics for the brain is heavily restricted by the blood-brain barrier. Only 1 to 2% of large molecules can successfully navigate across it to reach their targets. We can map the classical control block diagram onto the modern biotech pipeline. The aerospace controller is replaced by a generative AI model. The physical plant becomes an automated wet lab, and mechanical actuator limits translate to biological developability constraints, like the blood-brain barrier. Traditional biological R&D relied heavily on open-loop guessing, screening massive natural libraries and hoping for a hit. The new architecture operates as a closed loop. Treating protein engineering strictly as a control theory problem shifts drug discovery away from brute force screening, turning it into an exercise in predictive mathematical navigation. This closed-loop biological pipeline starts with generative AI models proposing novel protein sequences based on target structures. The sequence space for a single antibody contains roughly 10 to the power of 100 variants. The AI must search this space while simultaneously balancing competing objectives like binding affinity and thermal stability. This visualization illustrates the computational filtering phase, mapped here against Amazon's AWS biodiscovery benchmark. The system rapidly filters 300,000 raw computational candidates down to a refined batch of 100,000. This in silico triage operates at a speed that compresses what was historically a year-long physical screening process into a matter of weeks. The candidates then cross into automated lab systems for physical synthesis and assays. Crucially, the in vitro pharmacokinetic data is immediately fed back into the AI. Every physical test updates empirical data, continuously retraining the model for the next cycle. To prevent the biological equivalent of reset windup, developability constraints are embedded directly during the generation phase. The AI is restricted from proposing protein structures that violate the physical laws of human biology. By ensuring every physical lab experiment instantly retrains the model's internal assumptions, this active machine learning architecture collapses the standard 10-year drug development timeline. Executing this lab-in-the-loop engineering requires pharmaceutical companies to acquire massive data infrastructure. Algorithms alone are useless without high-throughput physical verification. To deploy this architecture, the industry navigates a strategic matrix, weighing capital expenditure against intellectual property control. In the build quadrant, giants like Eli Lilly construct localized AI labs. This demands millions for bespoke supercomputers, but lets the firm retain total proprietary control. This build-out is directly supported by hardware giants. NVIDIA is actively positioning pharmaceutical research to transition from traditional wet labs into localized AI computing platforms. Alternatively, the partner quadrant offers rapid deployment and shared risk, circumventing massive hardware costs. This is the model utilized in the recent co-development deal between Lundbeck and Cradle. In this framework, the trade-off is exact. Lundbeck leverages its highly proprietary central nervous system data, exchanging it for access to Cradle's external algorithmic specialization and generative models. An organization's ability to locate and secure its position on this infrastructure matrix directly determines its viability in the era of generative biology. For smaller organizations lacking deep intellectual property to protect or proprietary domain data to leverage, off-the-shelf cloud solutions firmly occupy the final buy quadrant. Whether stabilizing a fighter jet in turbulence or engineering a molecule to penetrate the blood-brain barrier, the underlying engineering achievements are parallel. Both rely entirely on the universal necessity of the closed-loop system to combat physical entropy. You cannot conquer a chaotic environment without continuously measuring it. Generating predictive data is no longer the true limitation to innovation. The math is proven, the algorithms scale. The ultimate bottleneck in modern research and development is simply the physical speed at which reality can be fed back into the mathematical model.